Welcome to week 2, a lecture in Advanced Foundation Mathematics, and in today's lecture we're going to be looking at basic mathematical operations such as addition and subtraction of algebraic expressions and also multiplication and division of algebraic expressions, among other things. So our first algebraic expression is 2x squared plus 3x minus 1. It is known as a trinomial because there are 1, 2, 3 terms. It's also known as a polynomial because all of the integer exponents are positive. So x squared, the 2 is positive, x to the power 1, 3x can be written as 3 times x to the power 1. So since all of the exponents are actually positive, it's also known as a polynomial. So our first term, 2x squared, can be simplified to 2 times x, where 2 and x are the factors of 2x squared. The second term, 3x, has factors 3 times x, and the third term is a constant value of -1. So if we looked at 4x cubed minus x squared, that's an example of a binomial because it contains only 2 terms. Hence, -3y to the power 2 is a monomial because there is only one single term. So hence another example of a polynomial which has exponents that are positive is 3x squared plus 2xy plus 1. Now in this case we actually have two variables. Y is also a variable as well as x. But because the powers or the exponents on all the variables are positive, hence this is another example of a polynomial. An example where the expression isn't a polynomial is this one, where the y to the power 1 is in the denominator. Using the index law, this can be rewritten as y to the power -1, so hence this expression is not a polynomial since y has a negative exponent. So now just summarising the rules that we use for addition and subtraction of algebraic expressions. So the first rule is gathering of like terms, and we define like terms as terms that contain factors that have variables to exactly the same powers. So for instance 6a and 2a are like terms because the variable a is to the power 1 in both terms, 6a and 2a, so hence we can add the two terms. 6a plus 2a is 8a. And for 5c and minus c, they are also like terms because the c variable is to the same power, it's to the power 1. So 5c subtract 1c is 4c. So when we gather up the like terms, we have 8a plus 4c. Now the distributive law, which is the next one, is one that's caused some problems on a couple of the diagnostic tests that I've looked at so far. And that is the one that basically says if you have a constant value in front of a bracket, then you need to multiply every term inside the bracket by that constant value. Now the negative sign outside the bracket really means that everything inside the bracket is multiplied by -1. Even though there isn't a coefficient in front of the bracket there's just a negative sign, it is implied that the coefficient is 1. We have one lot of a minus 3c in the bracket. So now multiplying each term inside the bracket by -1 Negative 1 times A is negative A, but negative 1 multiplied by negative 3C is positive 3C. So then moving on, using both those rules in conjunction, if we want to simplify 3C minus, in brackets, negative 2B plus C, we'll need to expand the bracket first. So negative 1 multiplied by negative 2B is positive 2B. Negative 1 multiplied by C is negative C. So then we need, once the bracket is expanded, we can then simplify or gather up the like terms. So 3C minus C will be positive 2C, and don't forget the plus 2AB. Now you can write that in either order because it doesn't matter which order you add terms. So it could be rewritten as 2C plus 2B. At the beginning of the second page, there is an example on expanding multiple brackets. In this particular case, there are 3 sets of brackets that need to be removed, so hence use the distributive law to remove the brackets. And once all of the brackets have been removed, you gather up the like terms to simplify the expression. Now it really doesn't matter whether you go about it by removing the outermost brackets first or the innermost brackets first, as long as you remember to apply the appropriate rules of multiplication and division when you use the distributive law. So now we're going to move on to the multiplication of algebraic expression, and this is where we apply the index laws from section 1.4, so from the previous week. So I'll just work through one example on this page, and let's look at the first example. We've got 2xy, then in brackets, multiplied by negative 6c cubed x squared, so we have two variables, c and x, but then also in brackets multiplied by 3xcy squared. So we begin by multiplying the coefficients, that is the constant values that are factors in the expression, and so we multiply 2 times negative 6 times 3 to give us negative 36. Then we begin with the first variable or pronumeral, which is x. X to the power 1 multiplied by x squared multiplied by x. There it's written there. And if you'd like to think about it using the first index law, that will be x to the power 1 plus 2 plus 1, so hence x to the power 4. Similarly, for y, we have y to the power 1 multiplied by y squared, so that's y to the power 1 plus 2, which is y cubed, and c cubed multiplied by c to the power 1, c cubed multiplied by c to the power 1 is c to the power 3 plus 1, c to the power 4. So hence the simplified expression is negative 36, which is the coefficient of the simplified term, x to the power 4, y to the power 3, c to the power 4. I'll leave you to have a go at example 2 on your own, and it's pretty well done for you there anyway. On the next page we are looking at expanding double brackets. So instead of just a single coefficient outside of a bracket, we have another bracket. So in brackets x minus 2 multiplied by x plus 6. In that case, every term inside the first bracket must be multiplied by every term inside the second bracket. So normally we begin with the first term inside the first bracket, x times the first term inside the second bracket, x times x is x squared. Then x times 6 is plus 6x. Negative 2 times x is negative 2x. Negative 2 times 6 is negative 12. So we come up with an expression, an algebraic expression with 4 terms, which we can simplify because 2 terms are alike. We have 2 x terms. 6x minus 2x is 4x. So the expression simplifies to x squared plus 4x minus 12. Now B is done for you, but C, where you have a coefficient in front of a bracket, and this is actually a double bracket because the whole thing can be rewritten as 3 outside of x minus 5. Now notice the bracket x minus 5 is squared, so we need to rewrite it again. Now in that case, what we would normally do is leave the 3 outside of a bracket. Now expand the 2 brackets, so we'll have, I'll use a different colour for this, x times x, x times negative 5, which will be x squared minus 5x. And then along the bottom, negative 5 times x, which is negative 5x. Negative 5 times negative 5 is positive 25. That's inside the bracket. So then you can see, to simplify, you still have the 3 outside of the bracket, so simplifying inside the bracket, x squared, gathering up the 2x terms, negative 10x plus 25. Now we need to expand that last bracket, so we need to multiply everything inside the bracket by 3. It'll become 3x squared minus 30x plus 75. So now moving on to the division of algebraic expressions, which is basically using the second index law. So for instance, with the first example, 15c to the power 7 divided by 5c squared. Now the first thing you do is look for common factors for the 2 coefficients. That's the 2 constant values that are multiplied by the variables. So 5 is a factor of 15. 5 divides into 15 3 times. So we can actually just do a little simplification there, like so. So hence the coefficient for the answer is 3. Now using the second index law, the exponent in the denominator, that is the divisor, will come up to the numerator and change sign to become negative. So we have 3c to the power 7 minus 2, that's 3c to the power 5. And we can do this longhand if you would like to, and that's 15 over 5 times c written 7 times. How many times is that? 1, 2, 3, 4, 5, 6, and once more, divided by c squared, which is c times c. So we get a little bit of cancelling out going on there. So that's our 3 coefficient, and a couple of the c terms will cancel out, and then we're left with c times c times c times c times c, c multiplied 5 times, so c to the power 5. So the answer becomes 3c to the power 5. B is again done for you, and having a look at C, if you have a divide sign underneath an algebraic expression where you've got additions and subtractions going on in the expression, then that divide sign implies that all of the numerator, all of that algebraic expression is in a bracket. So that means you need to evaluate it before you can actually simplify it. Now if you look at that expression in the numerator, none of those three terms are alike. So you've got an x cubed y term, there is no other x cubed y term there. Similarly, there is no other x cubed y squared term and no other x squared y term. So you're not able to simplify, but you can expand that bracket. And you can do that if you realise that the denominator is actually, can be written as 1 over 2x squared y, and then that can be what is then being multiplied by the entire bracket. So you can expand that bracket by realising that you have a term which is actually multiplied by the bracket, and that term is 1 over x squared y. So then if you actually do that multiplication, you end up with 2x squared y beneath each of the terms, because that multiplied, let's do it with a colour, that multiplied by the first term will give you this. That multiplied by the second term will give you that. And that multiplied by the third term will give you that. Now then you can go through and simplify. So for instance, if you look at the very last two, they're exactly the same. 2x squared y, get my pointer going here, 2x squared y divided by 2x squared y, well, they're actually going to cancel out. So you'll end up with 1 and 1, so you're going to have a plus 1. I think this one goes over the page from memory. Oh no, actually I'm asking you to do it. So let's have a look. So, for instance, the first term, 4 divided by 2 is 2. Then we've got x to the power 3, bringing up the x squared, the exponent changes sign, and then we've got y to the power 1 in the numerator and y to the power 1 in the denominator, so they actually divide out. In the second term, we've got 8 divided by 2, so that's 4. Then we've got x to the power 3 minus 2, y to the power 2 minus 1. And remember, we've already cancelled this one out, so that's just plus 1. So now simplifying the previous line of working, by evaluating those exponents, we will have 2x to the power 1, so we can just write it as x, y to the power 0. Now y to the power 0 is 1, so we can actually remove that, because anything multiplied by 2x multiplied by 1 is just 2x. And then we've got negative 4. X to the power 3 minus 2 is just x. Y to the power 2 minus 1 is y to the power 1 plus 1. So you can see that's quite a bit simpler than the original expression. On the next page we are going to solve equations. Now an equation is an expression which has a left-hand side and a right-hand side separated by an equal sign. On the left-hand side, in this case, we have an unknown. It's x. And call it a variable or call it a pronumeral if you wish. So 3x equals 24. So we need to find x, but we're multiplying it by 3 on the left-hand side. So if we undo multiply by 3 by performing the inverse operation, which is divide by 3, and we do exactly the same thing to both sides of the equation, divide both sides of the equations by 3 so that the equal sign remains valid. What will happen on the left-hand side is the 2 3's will cancel out just to leave you with x, and 24 divided by 3 is 8. So the solution to the equation in this case is x is equal to 8. Now there was only one operation performed on x in this equation. If there are multiple operations such as multiple additions or subtractions, multiplication and divisions performed on the variable in an equation, then you need to solve it by undoing those operations by performing the inverse operations, but in the reverse order of operations. So let's just think back to order of operations. It is brackets, exponents, division, multiplication as it occurs from left to right, addition and subtraction again as it occurs from left to right. So if you have an expression that you need to evaluate, then you work in this order. You evaluate your brackets first, then your exponents, division, subtraction in the order it occurs from left to right, addition and subtraction in the order it occurs from left to right. However, if you have an equation that you need to solve, you work in the reverse order. You undo any additions and subtractions before you undo any multiplications and divisions. And if you now work through, and most of the working is done for you, the next example on this page, you can see that that's exactly what's happened here. Once the bracket has been expanded using the distributive law. Now on page 5 we have an example of an equation, and this one is rather tricky, remembering what I've just said, and that is that you need to actually solve it by working in the reverse order of operation. So we need to undo any additions and subtractions before multiplications and divisions. What you need to remember with this one is that all of the operations on the top line, that is in the numerator, are actually inside another bracket. Because you've got the divide sign underneath the whole of the expression, there is an implied bracket around 4 minus 2 in brackets 7 minus p. So that means the very first operation we need to undo is divide by 5 in this case. So we can do that by multiplying both sides by 5. And on the right hand side, 5 divided by 5 is 1. So we just come back with the original expression that was the numerator, and on the left hand side 5 times 2p is 10p. So then it's just a matter of expanding that little bracket, making sure all of your variable terms are on one side of the equation, so in this case the left hand side, all of the constants on the other side of the equation, and so hence you can then go on and solve for p, taking account of performing inverse operations in the reverse order of order of operations. When evaluating and transposing formula, you're doing exactly the same thing as solving equations, because when you have a formula, you generally don't have many numbers involved. You just have a lot of variables. So for instance, our first equation is E equals mc squared, the relationship between energy, mass and the speed of light in physics. So we need to rearrange to make m the subject of the formula. That's what we're asked to do. So we need to rewrite the equation such that m equals something, and to do that rearranging, we must then also remember to work in reverse order of operation. In this case, there is no addition or subtraction occurring in the original equation, but there is a multiplication occurring. M is multiplied by c squared, so we divide both sides by c squared, and we will come up with m is equal to E over c squared. To make c the subject of the formula, then we need to undo the exponent as well, but remember you can only undo that after you undo any division or multiplication. So by dividing both sides by m, let's just do it here because you're probably not following this very well. So we've got E equals mc squared. We want to make c the subject, dividing both sides by m. The m's will cancel out on the right hand side, so you'll have c squared equals E over m, but you're asked to make c the subject, but you've got c squared as the subject, so now we've got to undo the exponent. So undo c squared by finding the square root of c squared, which will give us c, and then on the right hand side is the square root of the entire expression, E over m. Notice how the square root sign goes over the top of both terms, not just the top term, so be careful of that kind of thing. On the next page there are a couple of examples of transposing formulas and changing the subjects, and I'm not going to work through these. I'll let you work through them on your own. The answers are actually given in each case, and there are also a set of work solutions available for you if you get stuck. So now moving on to the next page. On page 7, we're going to remind ourselves of the Cartesian coordinate system, or it's also called the rectangular coordinate system, and this is where we plot the variable x on the horizontal axis, the variable y on the vertical axis, and hence we can have a two-dimensional graph point plot. So if we are given the ordered pair 3, 2 in brackets, the 3 is the x coordinate, the 2 is the y coordinate. So we can think of taking 1, 2, 3 steps in x, 1, 2 steps in y to get to the point which has the coordinates 3, 2. The x-axis, that is the horizontal line there, has formula y. The value of y is 0 everywhere along that line. Okay, that's the only rule that applies to that line. Similarly, the vertical axis, the y-axis, has the formula x is equal to 0. If we wish to draw the line y equals -4, or y is equal to -4 along a horizontal line, like so, and then also draw the line x is equal to 2, well, x is equal to 2 is there, so the line that has that rule is that vertical line through there. Give it the equation, x is equal to 2. Where the vertical and the horizontal lines intersect, that is the blue ones, we have the point with coordinates 2 for x, -4 for y. So the ordered pair 2, -4. So that's the answer to this one. The two lines cross at 2, -4. So then I've asked you to plot that last point. Now this time the x-coordinate is -3, so that means you're going backwards in x. So going backwards 1, 2, 3, and then y is 5, so that's going up 1, 2, 3, 4, 5. So there is the point, -3 for the x-coordinate. Can't draw that very well. Let's try that again. Rub it out and try it again. -3 for x, and for y we've got 5. Now we're going to have a look at equations, such as equations y is equal to 2x. That is an equation that is a rule between y and x. Once we know the value of x, we can determine the value of y by multiplying the x value by 2. Now, because we have just had a look at the Cartesian coordinate system, where we plot our y values in the vertical axis and the x values on the horizontal, I can actually plot this line on a Cartesian coordinate system. But I need to determine some points that will lie along the line, so I can apply any value I wish to x. So for instance, if x is equal to 3, then y is equal to 2 times x, which is 2 times 3, so y is equal to 6. So we have the ordered pair 3, 6, the coordinates 3, 6, which lie on the line. And if you have a look down here, I've actually written those in. Now I know that the rule is y is equal to 2x, but I can also say that y is equal to a function of x, so y is equal to a function of x, and the function of x is multiply it by 2 to find y. So in function notation, it sounds a bit roundabout, but we say that y is a function of x, so y equals f of x. We plot the value of f of x on the y-axis. So for instance, therefore I can find the value of y when x is equal to 0. When x is equal to 0, you know that y is going to be 2 times x, which is 2 times 0, which is 0. So hence, on our table of values, we can put in the value of 0 for y, when x is 0. When x is equal to -2, So we say, what's the value of the function when x is equal to -2? So that's the value of y when x is equal to -2. So it'll become, again, 2 times x is the rule. 2 times -2 is -4. So the value of y, the value of the function when x is equal to -2 is -4. And similarly for our last point, when x is equal to 4, we plot the function. When x is equal to 4 in y, it's 2 times x is the rule. 2 times 4 is equal to 8. So there's my point 8. Okay, so now if we plot those points as ordered pairs on a Cartesian coordinate system, let's plot them. We've got the first point, 0, 0. I'll just put it in the middle there. Usually you write the coordinates next to that point. We have the point -2, -4. So that's down here. Oops, get the pen working. So coordinates -2, -4. And then we have coordinates 3, 6. X is equal to 3, y is equal to 6. And the last one, there it is, ordered pair 4, 8. What do you notice about all of those points? And if I had a nice straight ruler, they'd lie on a nice straight line, which follows the rule y is equal to 2x. So I can actually write that this is equal to y, which is a function of x, which is equal to 2x. It's known as a linear function. There it is there, a linear function. That means it's a straight line. And notice it's an oblique straight line, and that the straight line also joins all points of the function. So now if I want to assign any particular value to x, I can also predict, therefore, the value of y that corresponds to it. So now we're going to have a look at function definition. F of x is said to be a function of x if for any value of x there is only one corresponding value of f of x, or if you like, only one corresponding value of y, which is then plotted on the y-axis against its corresponding value of x. So if you think about it, once you know the value of x, so if we say x is equal to 5, there is only one corresponding value of y that goes along with it. For our previous example, f of x is equal to 2x, that value would be 10. In the Cartesian coordinate system, we refer to the x variable as the independent variable, that is, we can vary it at will, and the value of y is dependent on that variable. So once we assign a value for x, the y value depends on the x value. All linear functions have the general equation, y is equal to mx plus c. That's really important. Let's put that in a square box. And that's the rule that links x and y. Remember on our previous page, the rule was y is equal to 2x. The value of m was 2. The value of c was 0. Now in this equation, the m is generally a constant term, as it was in our initial equation, and it gives us the gradient or the slope of the line, and C is the y-intercept. It's the point on the y-axis where the oblique line intersects the y-axis. So now we're going to have a look at an example, and we're given an oblique line here, and we're asked to find its equation. Okay, so if we have a look at the line, we have one point on the line with coordinates 6, -6. We can also see that that line crosses the y-axis at -4. So we already know the value of the y-intercept. There it is there. It crosses the y-axis at -4, so that point has coordinates 0, -4. It also means that we have 2 points on the line. So that means we can now find the gradient of the line, and the gradient is given by the rule y2 minus y1 over x2 minus x1. So that's the y step over the x step. So if I take, let's change the colours here, let's get a nice green going, make this point y1 and this point y2, then I can look at y2, the y coordinate of the second point is -6, there it is. The y coordinate of the first point is -4, so -6 minus -4. The x coordinate of the second point is 6, 6 there. The x coordinate of the first point is 0. So hence, when I evaluate all of this, I'll get a gradient of -1/3. So now, going back to the original equation, which remember was y is equal to mx plus c, I've determined that the gradient m is -1/3, so -1/3 times x, and the c value, the y-intercept, was -4. So the equation of the line is y is equal to -1/3 minus 1/3 x minus 4. To rewrite it without any denominators, I can multiply all terms by 3, so it would then become 3y equals -x minus 12. It's exactly the same thing, just multiplied by 3. Now on this page we are given a linear function, and we need to find the gradient of the line and the x and the y intercepts and plot the line on the grid below. The equation is 4x plus 2y equals 14. Now we need to rearrange it to get it in the form y equals mx plus c, that is, make y the subject of the formula. And once we do that, of course, we can then read off the value of m, the gradient, and c, the y-intercept. So our value of m is -2. So that means for every 1 step increase in x, there's a 2-step decrease in y. The y-intercept is 7, so hence the point 0, 7, that is, when x is equal to 0, y is equal to 7, lies on the graph, and it is the y-intercept. And for every 2-step increase in y, there's a corresponding 1-step decrease in x. That's exactly the same as saying that for every one-step increase in x, there's a two-step decrease in y. What it means is that as x increases, y decreases, or as y increases, x decreases. So then moving on to find the x-intercept, well, we know that everywhere on the x-axis the equation is y is equal to 0. So then we substitute y is equal to 0 into the equation, rearrange it to solve for x, and we've got x is equal to 7 over 2 or 3.5. So therefore we know that we have the point 3.5, 0, and that is the x-intercept. So now we can plot both those intercepts. So we'll plot the x and the y-intercepts, labelling them with their coordinates, and then join those 2 points to plot the line. So there is our Cartesian coordinate system here. So let's plot the first point, which is the y-intercept. So there it is at 0, 7. And the x-intercept, I'll do this one in red, and that is 3.5. So 3.5, 0. Now let's get a nice straight line through those 2 points. Arrows either end to indicate that it goes on to infinity both ways, and that is the line with the equation negative 2x plus 7. So you can see from that line that as x increases, y decreases, or if you like, as y increases, x decreases. Now there's not a lot of point to doing all of this linear algebra unless we can apply it to a real life situation. So we're going to do exactly that. The temperature of the Earth's lower atmosphere decreases with height above the Earth's surface according to a linear model, at least for part of the increase in height. If the temperature is negative 20 degrees centigrade at 7 kilometres and negative 63 at 12 kilometres, this is the typical height of flight of most commercial aircraft, find the linear model of the association of height and temperature. So instead of calling the variables x and y, we've called them h and t. Now we need to decide which of the two variables, height h or temperature capital T, is the independent variable, and which is then the dependent variable. If you think about it, the temperature is dependent on height above sea level. So once you determine the height above sea level, then there is a temperature associated with it. So hence we're going to make the height the independent variable. So h in place of x, it's the independent variable, and capital T in place of y in the model. Y is equal to mx plus c. So hence we'll now have instead T equals mh plus c. So we're using the variables t and h. We're given 2 points, and the points are 7 kilometres and negative 20 degrees centigrade, 12 kilometres and negative 63 degrees centigrade. So now we can find the gradient. So in place of y, remember we have t, in place of x we have h. So using the two values we have for temperature, there and there, in the equation for gradient, and the two values we have for height, we can come up with a value of negative 8.6. Now what does that mean? Remember we had temperature in the numerator, so we can actually put in some units here. We can say this is degrees centigrade per kilometres. Remember kilometres were in the numerator. So we've got a value here of negative 8.6 degrees centigrade per kilometre. That negative sign means that as we increase our height above the Earth's surface, the temperature decreases by 8.6 degrees centigrade per kilometre increase in height. So on the next page we're first asked to plot the 2 points and draw the straight line between them. So let's remember that we've got temperature on the y-axis, height on the x-axis, so taking the point was the first point, 7 kilometres and negative 20 degrees. So we've got this point here, coordinates 7, negative 20. And the second point was 12 kilometres and negative 63. So 12, negative 63. And just so that I get this line in accurately, there was a third point, if you remember. We had the y or the t-intercept at 40.2. So we have that point over there with coordinates 0, 40.2. Now I should be able to draw a nice straight line between all of those points. There it is. Isn't that beautiful? And that's the straight line. T is equal to negative 8.6 times h plus 40.2. Okay, so now let's see if we can answer the questions that are asked. Some discussion model questions. Can you use this model to predict the temperature at sea level? Well, sea level is when height is equal to 0, and if you think about it, we determined a temperature when height was 0. So this is 0 height, and we've got a temperature of 40.2. And if you think about it, everywhere on the Earth's surface, the temperature at sea level isn't 40.2. So this model really breaks down once I go beyond the 2 points that you were given, that is 7 and 12 kilometres. And so if we now have a look at it, the model really only works between the points 7 and 12 kilometres. I can draw the line below 7 kilometres, as I have back here, and get a value for the temperature at sea level, but it's really only useful for the equation for the linear part of the domain. What's the next question? I can't see it. What happens when height is negative? Well, have a think about it. When height is negative, that is, let's just fix that. So height is negative, is over this direction, and you can see from the model, even though I haven't given you the axis, the temperature is actually going to increase. And if you think about that, that actually does happen. The deeper you go in the Earth's crust, okay, so negative height means going down underground, and the deeper you go underground, the temperature does tend to increase. So that's the end of our lecture for this week. There's quite a lot in it, and I'll catch up with you next time. Bye.